tube have a good contact with this part here, and then cool down the helium, the mixture that's coming. The mixture comes here inside, and then here's an impedance. We have also an impedance there, and then come down. And here, these lines here are the heat exchanger. You have a continuous heat exchanger there, and then you have a step heat exchanger. It's really a tube with some sinter material inside, yeah. And you flow the mixture through this heat exchanger, and first down, yeah, to the mixing chamber. This part here is the mixing chamber. I explained yesterday, you guys, and then you have these two phases from helium-3 and helium-4, yeah, and you pump out from the other side. You pump out this mixture, yeah, and you go again through the same heat exchanger, yeah. The heat exchanger, you have to imagine, this double wall. The mixture that come out cool the mixture that's coming inside. Yeah, it's a double, so a system that you cool, and one thing help the other, yeah. And then you pump the mixture out until this steel here, and pump. In principle, what's happening is the following: in this steel, we are pumping with the turbo pump, yeah. And if you pump here out, because this phase here, I can explain later again, but this is a phase we call a dilute phase. It's a phase with helium-3 and helium-4. You know, and here in the steel you pump atoms from helium-3 out, because you can ask why you are pumping helium-3 and not helium-4, because it's a mixture. At this temperature, it is cold, the pressure, the vapor pressure from helium-4 is much bigger than helium-3. That means if you pump 99% helium-3, yeah, and the helium-4 stay there, and the helium-3 is pumping out. Because you are pumping out, you create osmotic pressure. The helium-3 that's on the bottom begins to migrate for the other region because you have to have all the time the same concentration for helium-3 and helium-4, and then you begin to create what you call an osmotic pressure, and this pressure comes from the bottom, because here you have, let's say, 6% helium-3, and here you have 1% helium-3, and then if you pump out and from 1% come from 1 to 0.9, you have to this should be constant, and then of course the other atoms from helium-3 migrate, and you have all the time 1%, and you have this migration. You create this osmotic pressure down. Let's say they come from the bottom up, yeah. And what happens? You have one in the mixing chamber. You have really a very pure phase from helium-3 on the top, and the other phase, that's this phase from helium-4 and helium-3. And what happens is the atoms from helium-3 from the pure phase will spring for the other phase, yeah, because as said, you have this pressure, you are pumping out with helium-3, and this cooling happen in the mixing chamber. You can imagine something like that. I don't know if you can see in the drawing. Here you have your phase boundary with two phases, helium-3 and helium-4, and if you pump on the top here, the helium-3 migrate from one phase to the other, and you pump out, yeah. That means here you have the cooling, yeah. And this helium-3 that we are pumping out, you put inside the system again. You circulate, yeah. And again, if you circulate, you come down inside the system. It's pre-cooling the pulse tube, yeah, and you circulate all the time. In principle, it's a continuous mode. Yeah.
What is the pulse tube?
Yeah, the pulse tube. The pulse tube in principle is let's say it's
a compressor.
It's a compressor with you have this. Yeah, it's just
4 Kelvin.
Yeah, it's just inside. I think the theory for a pulse tube I cannot give you here. It's a complicated thing, but it's just, you can buy also just the pulse tube with the two stage, or you can buy also pulse tube only with one stage. Then the first stage have only 50 Kelvin, and you have two stages. One achieves 50 Kelvin, the other achieves 4 Kelvin. Yeah, and what you do is expansion inside the expansion, and you cool the helium gas. You have helium gas inside, and you cool by expansion. It's like pistons inside, and I think it's a traditional. You learn that in thermodynamics. And you can have the two stages. If you have a two-stage pulse tube, one at 50 Kelvin, one at 4 Kelvin, and you use in principle this 4 Kelvin plate, yeah, to cool down this mixture that's coming inside. Yeah, this is what I said here. The mixture coming inside, and this is pre-cool here in your second stage, your 4 Kelvin, and you come inside the same. So after that, you have you pre-cool, and then you have an impedance. Yeah, with impedance, what happened? You have a small, let's say impedance. I don't know. Another is something very thin, and then you make a pressure in one side, and the other side comes liquid. You make an expansion, yeah, and then after the impedance, you have liquid coming out. Yeah, of course, by beginning, if you are at 300 Kelvin, it's not a liquid, but the temperature begins to decrease, and normally you begin really this circulation from mixture to the impedance below 10 Kelvin. Yeah.
Пожалуйста, спросите, какое там давление, мощность компрессора?
Которого? Вот верхнего?
Верхний, который вот...
What is the power of this
compressor? We call about how much power we can give in this second stage. Yeah. We tell about we can give 1 watt, yeah, and we achieve if I'm right 4.2 Kelvin, no 5 Kelvin, for example, for 5 Kelvin if you put 1 watt in the second stage. You have a heater in the second stage. If you put 1 watt, the temperature will go to 5 Kelvin. Yeah, we call all the time.
Ты про эту мощность спрашиваешь? Ты про тепловую, которую он рассеивал, или мощность?
Не, мощность компрессора.
He asked about consumption power of the compressor.
Нет, он 1 Вт рассеивает, вот на компрессоре мощность...
Что?
Андрей, мощность газа рассеянного...
Нет, ты
вот,
кладешь
нет, я понял. Газ поднимается вверх и отдает 1 Вт мощности.
Тепла
1 Вт, да, тепла 1 Вт в компрессоре.
Да.
А мощность компрессора? Ну, просто интересно.
Там 6 Вт.
What is the consumption power?
Yeah, this is I think